Hello everyone, this is Dr. Alok Agrawal and I welcome you all on our next video of fluid mechanics with subject code ME404. So in last class we have seen viscosity. We derived a very important equation, that is Newton's law equation, that established relationship between shear stress, dynamic viscosity and velocity gradient. We have also seen the effect of temperature on viscosity and we have seen what are the various type of fluids. Okay, so in this class, we'll use that Newton's law of equation and we'll solve two important problems related to that. So this lecture, video lecture will be on numerical on viscosity. So let us start with our first numerical. See what it is given. It is given that if the velocity distribution over a plate is given by u is equal to 2 by 3 y minus y square. Okay, so here it is given that velocity distribution is dependent on y, that is the distance from the fixed plate, in which u is the velocity in meter per second, the unit of velocity is given, and second at a distance y meter above the plate. So y is the distance over the plate, fixed plate. Okay, so we have to determine the shear stress at two different locations. First at y is equal to 0 means on the plate itself, and second at a distance of 0.1 by meter from the plate. Dynamic viscosity of fluid is given to be 8.3 poise. First, we have to convert this poise in SI unit, that is Newton second per meter square, that we have discussed how to convert it in our last class. So let us start with writing given. So the first thing is given is velocity profile, that is u is equal to 2 by 3 y minus y square. So from this velocity profile, we can calculate velocity gradient, that is du by dy, which is equal to 2 by 3. If we differentiate this with respect to y, we get 2.3, 2 by 3 minus 2y. So we have velocity gradient. Now, as per given condition that we have to calculate the shear stress at two different locations at y is equal to 0 and at y is equal to 0.5. First, we have to calculate this velocity gradient at y is equal to 0. By substituting the value of y as 0, we get du by dy as 2 by 3, that is 0.667. Okay. Again, by substituting the value of 0.15 in the equation that we have get du by dy velocity gradient, we'll get du by dy at y is equal to 0.15 as 0.367. Okay. Now viscosity is given 8.63 poise. So if you convert it in SI unit, we have to divide it by 10 and we will get 0.863 Newton second per meter square. So now coming to the calculation of shear stress, we know by Newton's law of viscosity, shear stress tau is given by mu into du by dy. And when we calculate it for y is equal to 0, we have to take du by dy as 0.667. Okay. So substituting mu is equal to 0.863 multiplied by 0.667 from here, we get shear stress as 0.5756 Newton per meter square. Again, now we have to calculate shear stress at 0.15 meter, y is equal to 0.15 meter. So we will take du by dy at y is equal to 0.15, that is 0.367. And substituting the value, mu will remain unchanged, that is 0.863 multiplied by 0.367, we get shear stress as 0.3167 Newton per meter square. So this is very simple problem. It may be asked in your exam. Okay. Now moving to the second problem, it is more important problem as per exam point of view. Here it is given that a cubical block weighing 4.5 Newton and having a 40 centimeter LH is allowed to slide down an inclined plane surface making an angle 30 degree with the horizontal. See, a lot of information is given in this sentence that there is a cubical block, means it has 6 faces and all the faces are same. Its weight is given, that is 4.5 Newton. Its length, edge length is given 40 centimeter, and it slide down an inclined plane having an angle of 30 degree with the horizontal, on which there is a uniform layer of oil that is 0.005 centimeter thick. So there is a sliding inclined plane surface which is at 30 degree angle with horizontal, making an angle of 30 degree with horizontal, having oil of thickness 0.005 centimeter. In that, a cubical block of 4.5 Newton weight is sliding having an edge length of 40 centimeter. Okay. Here the velocity of block is given 12.5 centimeter per second, and we have to determine the viscosity of the oil. Also, it is given, it is asked to express the kinematic viscosity. Once we will able to derive, we will be able to calculate the dynamic viscosity. Then we have to calculate kinematic viscosity, and we have seen that kinematic viscosity is a ratio of dynamic viscosity to the density of fluid. So density is given. Once we calculate dynamic viscosity, we can calculate kinematic viscosity. But here again, we have to calculate this kinematic viscosity in Stokes. Okay. So let's start the problem. First, let us draw a figure to visualize the problem in a better way. So there is an inclined plane surface which is making an angle 30 degree with the horizontal. Okay. In that inclined surface, a cubical block is moving. Here it is showing in the form of plate because we don't require other surface of the cube. We only have to deal with the surface which is in contact with the oil. So a cubical block of 4.5 weight is sliding down this horizontal inclined plane, making angle 30 degree with the horizontal. And the velocity of this block is 12.5 centimeter per second. And in between this block and this inclined plane surface, there is a oil of uniform thickness 0.004 centimeter thick. And we have to calculate the viscosity of that oil. So these are the given condition where angle is alpha is 30 degree, dy thickness is 0.005 centimeter. We have to convert each and everything in meter. Okay. Velocity is given 12.5 centimeter. Again, it is divided by 100 to get it in meter per second. And density of fluid is given 800 kg per meter cube. Now let us come to the problem that what is the force component of C? The weight component is acting vertically downward, but we are not of any use of this vertically downward weight component. We have to take the component of this weight along the direction of flow of or the movement of this block. So the weight component of block among this plane is given by W sine alpha. We have W, we have alpha. We can calculate it, the component of weight in the direction of movement. And then we have to assume the linear velocity profile, and as per that, shear stress is given by Newton's law of viscosity, that is tau is equal to mu du by dy. Now, see, shearing force can be given by this. Tau is shear stress is shear force by area. So shear force can be written as this mu into u by y multiplied by area A. So we will get shear force, which is opposing the motion of the block. Under equilibrium means if the block is not accelerated, it is moving with a uniform velocity, and is it given that it is expected that steady state velocity means the velocity will remain constant, it will not change with time. So if the velocity is not changed with time, then we can consider that the block is in equilibrium, and the force or the load acting in the direction of motion of the block will be equal to the shear force, that is given by mu into u by y into a. Now substituting the value of W, alpha, mu we have to calculate, u 0.125 meter per second, y it is given 0.005 centimeter thick, so y will be 0.00005 meter, and area will be the phase which is in contact with the oil, that is 40 centimeter into 40 centimeter, that is 0.4 meter into 0.4 meter. When we substitute all the values here, see what I have told, I have substituted it, and we will take this mu in left hand side and rest of the thing in right hand side. We get dynamic viscosity as 0.0056 Newton second per meter square, which can also be written in the form of poise, that is 0.056 poise, by multiplying this by 10. Now we have to calculate the kinematic viscosity. We know that kinematic viscosity is the ratio of dynamic viscosity and density. Substituting the value of dynamic viscosity and density that is given in the problem, we get kinematic viscosity as 7 into 10 to the power minus 6 meter square per second. But here we have to calculate the kinematic viscosity in Stokes. So we have to multiply it by 10 to the power 4 to convert this meter square per second into centimeter square per second. And this centimeter square per second is known as Stokes. This is the CGS unit of kinematic viscosity. So kinematic viscosity we get as 7 into 10 to the power minus 2 Stokes. So these are the two very important problems that may be asked in your exam. Okay. So in next class we will discuss two more problems related to the viscosity. Thank you.